Got a great little mathematical induction proof question here. It's an inequality, which seems to be what most people struggle with. And we have to prove that 2 to the n is greater than or equal to n squared for this domain. The positive integers starting from 4. So 4, 5, 6, 7, 8, and so on. Okay. So how do we go about proving this? And why is it difficult? Well, before I actually start on the proof itself, I'm going to give a bit of an explanation of how I'm going to go about the proof. Now, there's a couple of different ways I can approach this. Okay, the first way is to start at the most natural place. You know, let's call that step 1, right? And then as you go along and progress in step 1, you run up against the problem. Okay, and when you get to that problem, you think, oh, okay, something's gone wrong. I need to do some other stuff. I need to do some other step in order to fix up what's gone wrong in step 1, and then once you do that other step, you bring that back, so you return to step 1, you continue it, and then after that you finish and you do your last thing, your conclusion. Okay, so you go step 1, you sort of realize you got a problem, do this second step, bring it back to the first step, and then you finish. Okay, now this way is fine, this way will work, but it's a little awkward, isn't it, that you're sort of starting one way and then you've got to stop it and pick it up again later. Now, how would you do it otherwise to make it a little more sort of logical or sort of neater, I suppose? Well, this result here, this step, if you're going to need it to prove this step, you could start off with that step. Once you establish that, then you can start off step 1 and you don't need to go do some sideways thing, because when you run into the problem, it won't be a problem anymore because you can use this earlier result that you proved, and then you can finish, right? Now, you can see both of these approaches have problems, okay? This approach has the problem of being sort of, you know, you have to break your logic, do some side thing, and then return to it. The problem with this is when you have a look at this, you think, why are you even starting here? It's not the most natural place to start. It's not obvious that this would be the most logical place, or that you would need this in your next step. So, you know, they've both got their issues. To make this proof a little neater and go a little faster, I'm going to go this way, and I'll try and point out the problem that would have come up if we'd done it, you know, normally and gone from step 1. Okay, so hopefully that'll make sense of why I'm about to start where I do. So I want to prove this inequality. Rather than prove that off the bat, I want to consider a different one. I want to try and prove that 2 to the power of n is not greater than or equal to n squared, but that it's greater than or equal to 2n plus 1 for the same domain. Okay. Now, turns out this is quite a lot easier to prove than the original one, but we're going to need this result, this inequality, to prove the whole thing. So let's start off. Okay. Now, how do I'm going to do this by mathematical induction. How does a normal proof by mathematical induction begin? Well, we have to test the first allowable value. So I'm going to do that. The first allowable value being n equals 4. Okay. So on the left-hand side, what have I got? That's 2 to the power of 4, which is 16. On the right-hand side, I've got 2 times 4 plus 1, which is 8 plus 1, which is 9. So sure enough, the left-hand side is greater than or equal to the right-hand side by quite a margin. Therefore, it's true for that value, 4. Okay, now what comes next in the proof? Well, we need our assumption. So this is the mathematical sort of inductive step, if you like. So I'm going to assume the statement is true for some arbitrary value that I like, and I'll call that k, where k follows the same rules that n is supposed to follow. So it's an integer, starts from 4. Okay, it's got to be no smaller than 4. Okay, so what does that look like? Well, I'll just swap out all my n's for k, so that's going to look like this. So this is what I'm going to assume is true, and now what I'm required to prove off the back of that is that it's true for the next value along. That's how all mathematical induction proofs work. Okay, so what does that look like? It looks like this: 2 to the k plus 1 is greater than, now this will be 2 times k plus 1, so that's 2k plus 2 plus 1, so that's 2k plus 3 once you collect your like terms. Alright, so this is what I'm trying to prove. Now, how I go about doing this is pretty straightforward, but I go through it anyway. Let's just consider what happens if I gather everything on one side of this inequality? Often that's easier, because if I gather the 2k plus 3 on the other side, what I'm going to try and do is prove that that's positive. And proving that something is positive is one of the easier things to do. Okay, so I'm going to consider 2k plus 1 minus 2k plus 3. Okay, so we can do a bit of expansion here. What's that equal to? That's 2 times 2 to the power of k minus 2k minus 3. Okay, now watch what happens. This step is really, really important. Okay, in order to use the assumption that I've got over here, this assumption here, okay, I'm going to notice that I've got a 2 to the k here, and I know that 2 to the k is bigger than 2k plus 1. Okay, so if I were to swap that 2 to the power of k out, swap it with 2k plus 1 minus 2k minus 3. Okay, now look at this with me. I just swapped that 2 to the k with a 2k plus 1, right? And 2 to the k is greater than or equal to, at least, 2k plus 1. So out of these two lines, this one and this one, which one would be bigger? Which one would be bigger than the other? And the answer is, well, if you have a look at just this part, right? This part here should be bigger than this part here, yeah? So therefore, as a whole, this whole line ought to be bigger than this whole line, right? So therefore, I can say that, and don't forget that this line is actually equal to this. So 2k plus 1 minus 2k plus 3, that should be greater than or equal to this line with the swap. So this I'm actually using the assumption here. So by assumption. Okay, so just watch out for this. This is a tricky part. People get confused. Going from here to here, right? I've got an equality that implies an inequality when I bring in the assumption. Okay. All right. So I've got that being greater than that. So I can progress now on this right hand side. Now that I've done my substitution, some of this stuff can be expanded and simplified out. So I've got 4k plus 2 minus 2k minus 3. Put that up here. Oh, get rid of this piece of paper. Do that. Okay. Now what have I got? What have I got next? I've got, well, if I got 4k minus 2k, that'd be 2k. 2 minus 3, that's minus 1. So now I've got this. This is what I had on the left hand side. I've got that being greater than or equal to 2k minus 1. Okay, but don't forget that k is not just any number, right? It's got to be greater than or equal to 4. That was the domain for k, right? So therefore, I can say that what's here on the left-hand side, I can do another swap, right? If I swapped k for 4, swap k for 4, which is going to become 8. This one. Right? Which line will be bigger? Will this be bigger or will this be bigger? They could be the same size if k was exactly equal to 4, but for all other values, 5, 6, 7, 8, 9, 10, and so on, this will be bigger than this, right? So this line again is bigger than that. Okay, right, I'm almost there. So I've got this being true, that it's greater than or equal to 7, and 7's a positive number, right? It itself is greater than or equal to 0, right? So now I've proved that this thing we had on the left-hand side, that's greater than or equal to 0. So now I can boot over this 2k plus 3 and put it on the other side. And this is what I got, okay? So now, that means, what does that mean? The statement is true for n equals k plus 1. That's what I was trying to prove here, right? How do I prove that it's true for n equals k plus 1? That's what it looks like. That's what it looks like, and that's what I've got here. Okay, excellent. So now I can conclude that by the principle of mathematical induction, and by the way, some people accept this as a sort of abbreviation, and they don't have to write extra stuff. Some people don't, so just check with your teacher, whoever's going to mark your stuff. But this is fine. By the principle of mathematical induction, I can go back to my original statement, which is this one: 2 to the n is greater than or equal to 2n plus 1. And I can say that that's true for all of the values that I proved it for, namely greater than or equal to 4. Okay, excellent. Now, I've just proved this result. So what? It hasn't actually proved for me what I'm after, namely this original question. 2 to the n is not greater than this guy, but n squared. Okay, so now that I've proved this result, okay, I'm going to store that away and keep that in my head. And now I'm going to tackle the original question in earnest. Okay, so let's get a new color here. All right, now, since this is a whole new proof in some ways, I'm going to start it like I normally would, which is to test the first allowable value. Okay, so what does that look like? I'm trying to prove 2 to the n is greater than or equal to n squared. So the left-hand side is 2 to the n, which is 2 to the 4, which is, again, 16. What's the right-hand side? It's n squared. So that's 4 squared, which is also 16. But that's okay, because I've got an equality on this boundary. So in this case, the left-hand side is still greater than or equal to the right-hand side. So it's true. 4n equals 4. Okay, that was my test. Now I'm going to assume the statement's true for an arbitrary value, which I'm going to call k, which again follows the same rules that we've been talking about. Greater than or equal to 4. And what does that look like? Well, it should be, let's see here. What was I trying to prove? 2 to the k, I think, was on the right-hand side, and greater than or equal to k squared. Okay, now that I've assumed that, what I want to try and prove is for the next value along, k plus 1. So what does that look like? 2 to the k plus 1, greater than or equal to k plus 1 all squared. Okay, now, in order to prove this, I'm going to pull exactly the same kind of trick that I did before, which is to consider what happens if I bring everything over to one side. Okay, so if I say, let's just have a think about this. 2 to the k plus 1 minus k plus 1 all squared. Now you can see, if I can prove that this is greater than or equal to 0, then I'm done. I can go home, because once I've got that greater than or equal to 0, I can move the k plus 1 squared over to the other side, and that's what I'm trying to prove. Okay, so how will I go about doing that? Well, I can do a little bit of simplifying here, right? That 2 to the k plus 1 means 2 to the k times 2 to the 1, right? So that's 2 times 2 to the k, okay? And what's this? This, I can expand this. This is k squared plus 2k plus 1. Okay, now, what can I do to work with this? Well, the first thing I want to notice is that my assumption, what I'm assuming here, has to do with 2 to the k, okay? And I have a 2 to the k here. I actually have 2 of them, okay? Now, for reasons that I hope will become clear in a second, I'm going to separate them out. I'm going to put 2 to the k here and another 2 to the k there. I've got this guy here. Okay, now, just like before, I'm going to swap one of these out for a k squared, okay? So let's leave that 2 to the k at the front the same, and I'm going to turn this 2 to the k into a k squared, okay? Now, remembering that I've assumed 2 to the k is bigger than k squared. Between these two lines, which one will be bigger? Well, this 2 to the k should be bigger than k squared. Everything else is the same, right? So this line ought to be greater than or equal to this next line that I've written, right? And don't forget that this is actually equal to this. Okay, so this is by assumption. I've just used the inductive hypothesis here. By assumption, okay, sorry, it's a bit, I need more space. By assumption, this is true because I've done this swap, okay? All right, well, you can see, where's this going? This k squared and this k squared will cancel, so I get 2 to the k minus, after I cancel these two guys, I'm left with 2k plus 1. Okay, now, you can see why I did this result before, because at this point, if we had started proving this, right, test the first allowable value and see where it goes, you'd run up to here and then you'd think, uh-oh, how do I prove that this is positive? Okay, and then you'd have to go off elsewhere and do what we did before and prove all of this stuff that it is positive, okay? But or rather that this part is greater than that part. So now that I've already proved that, I can say, wait, hold on a second, 2 to the k is going to be greater than or equal to 2k plus 1. That's what I went and proved in the first stage of my proof. Okay, so therefore, if this number is bigger than this number, the whole thing ought to be greater than 0. It should be positive, right? If you got a big number minus a small number, you're going to get a positive number left over. So it's got to be greater than or equal to 0. The only way that it would not be is if this number were smaller than this number. Okay, so now I'm almost there. I've had this on the left-hand side, right? So now all I need to do is kick this guy back over to the right-hand side of the inequality, and I get this. It's greater than or equal to k plus 1 all squared, which is what I was trying to prove, right? So the statement is true for n equals k plus 1, assuming you can assume that it's true for n equals k. Right, so that's it. I'm done now. By the principle of mathematical induction, including both of those parts of the proof that I used, I can say now that 2 to the n is greater than or equal to n squared for those given values. Sorry, that's a 5. Those given values of n. We're finished.